Hello, my name is Bassam Burgan, and I'm Director of the Steel Construction Institute. In this presentation, I will discuss the construction of a building using modular steel plate concrete construction with the objective of quantifying the cost of SC relative to reinforced concrete, quantifying the construction schedule of SC relative to RC, providing feedback on manufacturing and construction quality, and developing steel concrete manufacturing and construction expertise. Now, first of all, to be clear about the form of construction, it is made up of two steel plates with shear studs welded to the plates and a concrete infill. And in this form, it is generally used for vertical elements, so for wall construction, and a single plate with shear studs and stiffeners, and then a concrete slab cast on top, and in this form it is generally used for floors. So this is the basic form of construction: steel plates, studs to both plates, and a concrete infill. But in this form, it presents a number of practical difficulties. What we need is for the two plates to be joined together so they can be handled, they can be moved around, they can be concreted without the need for any propping. And so the plates are generally joined either by bars welded to the two plates, bars bolted to the plates, ribs, or trusses between the plates, joining them together. The problem is because the space between the plates is so limited, some of these methods are difficult to make work in practice. And there's been a number of developments that have led to SC construction systems. One of them used friction welding, where the bar is spun at high speed between the plates, pressure applied to the plates from the outside, and so friction welds form either end of the bar to the plates. And this was the bi-steel system that was developed by Chorus in the 1990s. Another more recent system makes use of U-shaped plates that have the studs welded onto the plates, and then units like this are welded together to make up a module, and so the joint between the outer plates is integral to the module. And this was more recently developed by a company called Modular Walling Systems in the UK. Why the interest in this form of construction? Well, it has a number of advantages compared to reinforced concrete. The steel plates provide reinforcement to the concrete, so there is no need for the conventional reinforcing bars. The plates also perform the function of permanent formwork, so no need to add formwork and then strip it and do any patching up work afterwards. The plates provide confinement to the concrete, so that improves the properties of the concrete. And in some applications where a watertight membrane is required, that again is a function provided by the steel plates. The system lends itself to off-site fabrication, which generally means you can achieve better quality more easily because you are manufacturing in a factory rather than building on site. Because it's in a factory, it means better working conditions than site conditions, and speed because you can have parallel working in multiple factories, or you can start the manufacturing ahead of time. And then on site, this becomes a process of installation rather than construction, and you completely eliminate the need for embedded plates. Now, embedded plates are these things that are steel plates with anchors welded to the back, and these are used extensively in industrial buildings. They are fitted to the reinforcement in reinforced concrete, and their purpose is to provide support to heavy equipment, mechanical and electrical. In a nuclear power plant, there are typically somewhere in the region of 100,000 of these in the project. And they are very problematic because in a nuclear power plant, the density of reinforcement is very high. And so fitting these into the reinforcement always creates clashes and problems between the anchors on the back of the embedded plates and the reinforcing bars. Now, how do we design these structures? Well, there's been a number of design codes published around the world. The first one was a Japanese design code published in 2005. The second was a Korean design code published in 2008. And then an American specification, AISC specification in 2012. Notice all of these have been aimed at the nuclear sector. The Japanese code was updated a few years later in 2009, and the American specification was updated in 2018. In Europe, we coordinated a major European project between 2013 and 2017 involving the list of partners you see on the slide. And this led to the publication of an SCI design guide, which was based on the results of this research program. That design guide has since been evolved into a SEN technical specification, which we hope will be published sometime towards the end of next year. Some examples of where this form of construction has been used. First of all, in the nuclear sector, the first picture on the left is an application in Japan in 2002. The next one is in the AP1000, the Westinghouse reactor, and the first one of these to be built was in China, completed in 2018. And the system that I showed earlier, the steel brick system with the folded plates, is currently being considered for the small modular reactors being developed by AEG Hitachi. It's been used for bridge decks, and this is an example of a bridge deck in Japan constructed in 2012. And it's been used in the core walls of high-rise buildings. So there's two examples, one in Ireland in 2004 and in Birmingham 2007. And these used the bi-steel chorus system. The third one is a more recent example in the US. And this was a 52-story skyscraper, where using this system for the core walls enabled the construction program for the structure to be reduced by 10 months. And we are currently working on a design guide for the steel brick system for use in core walls, and this will be published early in the new year. Now back to the building that we constructed in this project. The building was a replica of the EDF diesel generator building. Now, these buildings were introduced on French nuclear power plant sites as a post-Fukushima safety measure, and they are intended to house diesel generators which provide power to the nuclear power plant in the event that all other means of power supply fail. We chose it because there are 58 of these buildings that have been constructed in reinforced concrete. So there's a lot of data to compare with how SC construction compares with reinforced concrete in terms of cost and time and so on. And it's a complex enough building to provide a real test for the system, but small enough to fit within the budget of a demonstration project. This gives an idea of the size of the building. It has a footprint of 24 meters by 12 meters, and it is just under 15 meters high. And this is the form of construction we used for the double skin. It's two steel plates with bars welded to the two plates and shear studs. And for the floors, a single plate with shear studs and T-stiffeners. And this was the project team. So SCI was in overall charge of the project as project coordinator. EDF acted as effectively the construction client, as well as being in charge of engineering coordination and development of the building information model and some instrumentation that was fitted into the building. Aegis was the structural designer. CEA monitored the design, manufacture, and construction with a particular focus on what is expected in the nuclear sector. ArcelorMittal provided advice on material selection and welding. The main contractor on site was Bouygues, and the fabricator of the module was Pecco. Now, if you're going to construct a building out of modules, one of the first things you need to consider is how you are going to break up the building into modules. And this is a balancing act between a number of sometimes competing factors. So first of all, there are issues to do with the building layouts. Where are the penetrations through the walls, through the floors? Do you have these completely enclosed within a module, or do you break them across modules? And what is the general layout of the building, the floors, the internal walls? You need to try and avoid having too many joints between modules being at the same location, because that complicates the join and could lead to congestion. There are fabrication shop considerations. So, for example, the crane capacity in the fabrication shop that is going to determine the heaviest module that you can fabricate. Issues of access and clearance in the factory. What's the maximum size of the factory gate, for example? What's the headroom in the factory? These modules take up a lot of storage space, so you need to consider that. And standard component sizes. So what's the maximum plate size that you have available to you? Because if you try and make the modules if you try to make the modules larger, then you will end up having to introduce butt welds into the plates all the way along their length, which adds to the fabrication cost and time. There are transportation consideration. Depending on how you're moving the modules from the fabrication shop to site. So if you're moving modules by road, there are maximum sizes that you can transport by road. And then there are construction site consideration. For the construction site, the site team would probably prefer to minimize the amount of site joining, which means having the modules as large as possible. They would want connections that are easy to make on site. They want fairly tight tolerances, so there are no problems with modules fitting together. And of course, there is the crane capacity on site that determines the largest module that can be handled at maximum reach of the crane. Now, we designed the building so that it was subjected to all the same actions as the diesel generator building. So it was the same loading, same equipment, the same accidental loads. But in addition, because the SC construction modules are going to start off as steel structures before they are concreted and they become composite structures, there are additional design conditions for the construction stage. So these all also have to be considered. And as a result of that, we determined the thicknesses of the walls, the floors, and the plate thicknesses, as well as the spacing of shear studs, spacing of tie bars between plates, and so on. And so generally, these were the sizes for the walls and for the floors. So 500 millimeter thick walls with 8 millimeter thick plates, and studs and bars spaced at 200 millimeters. And you can see on the right-hand side the arrangement for the floors, again, 500 millimeter thick concrete slab cast on an 8 millimeter plate with stiffeners and shear studs. We looked at a range of different ways of joining the modules together, because the purpose of the project was to try and understand the pros and cons of different joining methods on site. So some of these were mechanical joints without welding, some included welding. So for the first 4 levels of modules, there were 6 levels of modules through the height of the building. The first 4 utilized a dowel bar, which sits across the joint between modules. And so the connection between the modules is only made once the concrete is cast and has hardened. The top two levels were welded, and we used both fillet welded modules as well as butt welds. Again, to look at both methods, and in the nuclear sector, there are some areas, some particular parts of structures that have to be butt welded. I'll come back to this. For one of the walls, we used blind bolts to join the wall to adjacent modules. And then for the floors, we used a simple double angle cleat to join the T-stiffeners to the walls. And floor module to floor modules, this was not a structural connection, it was just a connection to fix the modules together. And these simply used a plate that covered the joint between modules and was clamped down with a channel. We made two changes to the building compared to the original diesel generator building, and this was to explore other applications for this form of construction. The first of these was a replica of the spent fuel pool in a nuclear power plant. So here, the internal plates had to be made out of stainless steel because these are the plates on the wet side of the structure. The external plate was carbon steel, so these were hybrid modules with stainless on one side, carbon steel on the other side. It had double skin floors because it's required to have leak tightness. So this was the only floor in the building that had a double skin construction. And there were leak detection channels introduced behind the joints between modules that are joined together on site. Again, this is a requirement for spent fuel pools in nuclear power plant. The other change we made was in the opposite corner of the building, and this was the introduction of very thick walls here, and these were introduced to represent the airplane crash shells that are used to protect the reactor in nuclear power plant. So here the wall thickness was increased from 0.5 meters to 1.3 meters, and the plate thicknesses were increased to 20 millimeters for the outer plate and 12 millimeters for the inner plate. And the purpose here was to investigate the fabrication and constructability on site of modules with much thicker walls and thicker plates. We developed a series of manufacturing tolerances, and you can see some examples here, and these were developed through discussions with the main contractor and with the fabricator to make sure that the main contractor is happy with those tolerances for site construction, and the fabricator can meet these in the fabrication processes. We used building information models throughout the development, throughout the life cycle of the project, from conceptual design all the way through to construction on site. And the model was developed initially from a conceptual design model where we just had volumes and openings as well as overall thicknesses, through to a basic model where we had the input from the finite element analysis and the initial design of the building, finally to a fully detailed model that included all the connection details, the ancillary components used to aid construction on site, module stiffening, lifting points, weld specification, everything was in that detailed model. With regard to module manufacturer, generally, we had bars welded to both plates. So as you can see here at the top and bottom, both ends of the bar are welded to the plate. For some modules, and this was specifically in the pool module, we had the bar welded from the inside to one plate and from the outside to the other plate. And this was because for one of the plates, it's not permitted to have penetration through the plate for the pool structure. And a third method used a threaded bar, which was screwed into a coupler in one plate and then held down with a nut at the other end. And this was used at the edges of modules that were joined by dowel bars, because these tie bars had to be removed for the installation of the dowel bars. Looking now at the module manufacture, we have the plates with the shear studs, but we also use these short stiffeners oriented in two orthogonal directions. And the purpose of these was to provide a surface for the second plate to be uh, uh, positioned on in order to enable the welding of the tie bars. And also to provide stiffness to the module, because if we just use tie bars, the module would not have sufficient racking stiffness and would deform during handling and transportation. Once the second plate is placed on top of the stiffeners, it's then welded. The stiffeners are welded from the outside to the plate, and then the bars are inserted and welded from the outside to both plates. So the sequence is we cut the holes in the plates for the bars, we weld the shear studs on, we weld the short stiffeners on, then we bring the second plate with the studs welded to it and place it on top of the stiffeners, and then we weld from the outside the second plate to the stiffeners, and then finally we insert the tie bars and weld them from the outside to both plates. And this video shows the manufacturing process for one of the modules. This is for the APC shell module, so it's one of the thicker 1.3 meter thick walls. So the second plate has been placed on now, and the welding operation is progressing from the outside. And this now completes the welding of this module. So that's how a plain module is manufactured. When we come to corner modules or modules that have internal walls as part of them, the process starts in exactly the same way, but in addition, we have now corners that we need to weld, which we don't have direct access to. So instead, these are welded from the outside using intermittent welds. So we cut slots into the outer plate and a sawtooth into the inner plate that fits into these slots, and then the welding is completed from the outside. And that, of course, has to be structurally verified that the intermittent weld is adequate for the corner. The tolerances were verified in a number of ways. We had templates created for every module, which showed the tolerance requirements for each part of the module, for every tolerance that was specified, and these were checked by hand and then recorded on the template. And in addition, a number of modules were selected for laser scanning, and these were laser scanned, and the results of the laser scanning were compared also with the manual measurements. Now, there were also a number of additional details introduced into the modules, either to facilitate the joining of modules on site or to facilitate the construction process on site. So first of all, for the modules joined by dowel bars, we have these removable tie bars that I mentioned. These, you can see them, they're They've been removed for the installation of those horizontal bars, which are the dowel bars, which are dropped down from the top into position, and the tie bars would be in the way if they were still in place, so they're removed for the installation of the dowel bars. Dowel bars are brought to site in these frames and installed as a group. We have these brackets to support these frames that hold the dowel bars together. And then for the vertical dowel bars at horizontal joints, these are delivered, installed into the modules in the fabrication shop. They are hidden inside the module during transportation, and then they are pulled up once the module is ready to be installed on site. We also have angles which provide temporary support to floor modules. So these are attached using studs that are welded to the surface of the wall modules. We have these nuts that are tack welded to the back of the plate in wall modules, and the purpose is to attach the double angle cleats to the wall on site. We have anchors inside the wall modules to provide continuity to reinforcement bars in the floors. And these are the details for the joints between floor modules that we saw earlier. And they are made again using threaded studs that are welded to the plate of the floor modules. There's also a series of ancillary components to help with the construction on site, and these were developed as part of a construction methodology. So there are these hard stops to help with the positioning of the modules at ground level, and erection guides also used at ground level. We have leveling jacks that are used to adjust the level of the modules once they are installed. Erection guides at the top of modules for the placing of the next module on top of a lower module. We have these brackets that are used with telescopic props to stabilize the module on site, whether in storage or when it's erected on the building before it's concreted. And all of these components are attached to the plates of the modules using threaded studs that are welded in the fabrication shop to the plates. Another set of components for holding the modules, wall modules together is angles that attach the modules together, and these components which are used for aligning the plates. These were used on the first level, and then we found that the tolerances were good enough that we did not require these for upper levels. Just a quick look at the fabrication effort required for these modules, and this is measured in hours per ton for a simple planar modules. So just a two-dimensional module, we were requiring on average 54.5 hours per ton. Modules that have inner parts, so such as the picture in the middle, these required 82.9 hours per ton. So that's 52% more than the planar module. And corner modules required the most in terms of fabrication time, 94.6 hours per ton, 74% more than a planar module. However, what we found, this was a new form of fabrication for Pecco, the fabricator. And what we found was that through learning as modules for different levels were manufactured, the fabrication efficiency improved significantly. So as we went up from level 1 to level 5, I'm comparing here the number of hours per ton. You can see reduced significantly, particularly for the more complex modules with inner parts and corner modules. Few module statistics. You can see there the heaviest module that was fabricated, 8.5 tons, the longest module, 10.5 meters, and the tallest module, just under 4 meters. In total, there were 158 modules fabricated for the building. And in terms of total weight of steel in these modules, 415.4 tons. And then in addition, there were 48.4 tons of ancillary components. These are reusable items, so they are taken off and they can be reused on future projects. The manufacturing of the modules took place in Lithuania. The construction site was in France, so the modules were transported from the factory in Kaunas in Lithuania to the construction site, which is about 60 kilometers southeast of Paris. They were transported in 37 lorries, 30 standard trucks, 7 oversized trucks, and 2 further oversized trucks for the longer modules. They were transported, some of them entirely by road, some went by sea initially and then completed the journey by road into France. The foundation for the building was a standard raft foundation. What was special about it was the need to position the starter bar very accurately, so we did not have any clashes between the starter bars and the steelwork of the modules. So the positions of the starter bars were initially marked accurately on the ground, and then a template was made that was used for ensuring that the positions and the spacings of the starter bar were accurate, also the verticality of the starter bars by having 2 layers within that template. And once the starter bars were installed, they were then tied in position in 2 directions to ensure that they did not move during concreting. Then the reinforcement for the raft was completed and concreted. And here you can see the installation of the first module being lowered by the tower crane, guided by 2 guys with ropes so they can do the guiding from a distance without getting too close to the module being installed. And then the next module, again being lowered into position over the starter bars, being pulled against these erection guides that we saw earlier. And you can see why it's important to have the starter bars installed very accurately. You have the plate very close to the starter bar, you have shear studs, you have tie bars. So in order to avoid any clashes, it is very important to coordinate this in the building information model and then to ensure that it is executed correctly on site. Once the modules are installed, they are then leveled using the leveling jacks that we saw earlier. And once they're leveled, they are then fixed in position using these props. Now, after the installation of the modules, for the modules that are joined by dowel bars, the next step is to install the dowel bars. And you can see dowel bars here being lowered into position at a vertical joint. So this is being lowered by the tower crane and maneuvered into position by an operator. And then you can see the dowel bars being positioned on those brackets that are welded inside the module. Now, for those joints, there is a small gap between modules, so that gap has to be closed in order to do the concreting. And initially, this was done just using conventional formwork at the joint. However, we found that this did not work very well in some places. So where there was leakage of concrete, we ended up with a joint that was of poor quality. Where there was no leakage, the joint was perfectly okay. But there was clearly a need for a different way of doing this, and so the site team then developed an alternative system, which was a steel plate, a thin steel plate that fitted on the inside of the joint, held in position using short studs and these little square plates. And this worked extremely well because it's on the inside of the joint, so the concrete pressure actually pushes it against the joint and helps to close the joint even further. And this was fine for the remainder of the project. Working up through the building for the upper levels is exactly the same, except we are now working on a working platform which is supported on the lower modules. So the working platform is installed, and then modules are installed um, into position over the dowel bars in exactly the same way as we saw on the ground floor. Installation of the floor modules again is done by the tower crane. First of all, the temporary support angles are installed on the module walls, and then the modules are installed between the walls onto these temporary support angles. Again, this proved to be trouble-free. It requires a careful tower crane operator because you're now installing modules within a confined space. And then once the module is installed, the T stiffeners of the module are attached to the walls using these nuts that are pre-welded in the fabrication shop onto the module wall plates. So the double angle cleat connection is made, and then the reinforcement for the slab is added. So it's screwed into the couplers in the walls, and then the reinforcement is completed, and the concrete floors and walls are concreted. For the upper level modules, we used welding. So some of the modules were fillet welded, some were butt welded. You can see here a module that has been installed with guide plates, which also act as backing plate for the fillet weld. Now, tolerances start to become more important for the welded modules. So here you can see an example of a module where there is virtually zero tolerances between the backing plate and the shear studs. And this clip shows the installation of a module that is to be fillet welded. And you can see the guide plates here fitting into the adjacent module. There was some preparation for welding to be done, partly because the modules were on site for a period of time without the edges to be welded being protected. So rust developed on those edges, and that had to be removed before the welding could proceed. Because of the way the backing plates were detailed, there were also some gaps that were there to avoid clashes between backing plates, and so these had to be filled. And now this is a detail that could have been avoided with slightly different detailing, and this is something that should be done on a future project because it took quite a bit of time to close these gaps on site. Once they were closed, it was then possible to concrete the modules. The fillet weld geometry was nominally a 30 millimeter gap between modules with a plus or minus 10 millimeters. I mentioned that we used a blind bolt for one of the wall modules, and you can see that here the holes were drilled on site for the blind bolts, and then the bolts were installed, and this proved to be a very easy connection to make, and was quite popular with the site team. Where the tolerances were most important was for the fillet welded joints. You can see an example here of one that is a half V joint and another which was a V joint. Now the issue here is that if you end up with a gap that is too small, you have a problem. If you end up with a gap that is too large, you also have a problem in that you end up having to put too many weld runs in order to fill up the joint, and that takes up a lot of time, and it's a lot of weld metal and potentially deformations due to welding and so on. The pool modules were assembled on the ground into larger modules. So every two modules were assembled into one larger module and then installed on site. So we had two modules for the floor that you can see in the middle picture. And then for each of two levels of the wall modules of the pool, there were again two U-shaped modules that were joined together to make up a rectangular module that was lifted and then installed in position. And then the pool module was concreted through the walls on one side. And the reason was that that was the only structure that had a double skin floor. So we wanted to do it this way in order to ensure that the flow of concrete through the floor pushes all the air out of the floor as the concrete rose through the opposite wall. And this is the completed building, which you can see there. In addition, we wanted to look in the project at how you would dismantle some of these structures. So we used a chainsaw to cut a door through one of the modules, and you can see the cut door there. Again, that technique proved to be quite straightforward to use for this type of construction. And it's interesting here because you can see the quality of the concrete around the shear studs, around the starter bars and the dowel bars. We also instrumented many of the modules for future monitoring of the building, and there's a module at ground level that was that had instrumentation installed, modules, floor modules at the top of the building, which will be mechanically tested in due course. And we also installed instrumentation into the two walls of the pool module. This shows the range of instrumentation that were installed. So strain gauges, vibrating wire gauges for measuring mechanical strains in the modules. There were modules, instrumentation installed to measure the development of the concrete strength. There were modules installed to measure aging of the concrete and corrosion of the steel plates on the inside. Finally, looking at how this project compared with the reinforced concrete diesel generator building, for levels up to 10.84, the two buildings were identical, and what we found was a 31% saving in time spent on site. For the upper levels, this is where we added the pool and the APC shell, so we made things more complicated in the demonstration building, but still the saving in time was 22%. In terms of workforce, on a typical reinforced concrete project, there was 30 people working on site. In the case of this demonstration project, we had 8 people working on site, plus 5 welders who were there for 1 month when we were welding the top 2 levels of the building. So a reduction of 73% in workforce. And in terms of number of hours worked on site, there was a reduction from 23,500 hours to 7,300 hours, a reduction of just under 70%. Comparing material usage, formwork is almost entirely eliminated. The only formwork we had was in the form of those narrow bars across the joints of modules connected by dowel bars. Concrete quantity was very similar because we didn't try to optimize thicknesses of walls and floors in this project. Reinforcing bars were largely eliminated except for the bars we used in the foundation and in the floors, no reinforcing bars in the walls. However, that was replaced by steel plates, of course, for the wall modules and for the floor modules. We had ancillary components that were part of the construction methodology, and we completely eliminated embedded plates. There were about 1,000 embedded plates in the diesel generator buildings. We don't need any of these in the SC building. So that concludes my presentation. Thank you very much.